this one's a little different than things that I'm used to, because most of the time it gives you a function, like an original function, but this one gave you the derivative. That's not f of x equals x minus 5. That's f prime x equals x minus 5 squared plus x, times x plus 9. So that step of finding the critical x's where you have to set the derivative equal to 0, that step's easier because we already have the derivative. So x minus 5 squared times x plus 9 is already factored for us. I chose to solve the x minus 5 squared like this, where you say the square root of both sides, the square root of 0 is 0, the square root right here undid the squared, so I'm just left with x minus 5, and I get a single answer of x equals 5. You could have approached that differently and said x minus 5 equals 0, and then x minus 5 equals 0 again, but you would have gotten the same answer. You would have got x equals 5 and x equals 5. But if that's the approach that you did, you only type 5 in once for your answer, because it's not useful. See, what I'm saying is x minus 5 squared could also be thought of as x minus 5 times x minus 5. So you could say x minus 5 equals 0 twice, which there's no use in doing this twice, because I just get the answer of 5, and I get the answer of 5 again. So if you were typing this into an answer blank, you wouldn't type 5 comma 5. You would just type 5, which is what I got over here when I did that method. But now that's just for that one side of that factor for the derivative. There's also a factor of x plus 9, so you have to set x plus 9 equal to 0 as well, and you get negative 9. So the critical x's occur at x equals 5 and x equals negative 9. I can tell where the original function, well, that's not the original, that's the derivative, but I can tell you about the original function by looking in between those critical x values. So on the number line, those critical x values are at negative 9 and at 5, and I did this in numerical order. And so I call this windows of opportunity, where we have intervals between these critical x's, and I want to test each of these intervals. So I chose to plug negative 10 into the derivative. Now negative 10, that's just a random number inside that interval. I did not have to use negative 10. I could have used negative 11, negative 12, negative a million, okay? But I just thought negative 10 was pretty easy. And whatever I get as the answer, whatever the sign is, that will tell me whether I'm increasing or decreasing. So since on that interval, I plugged in to the derivative and I got a negative, I know on that interval I'm decreasing, okay? So the next interval between negative 9 and 5, I plugged in a random number, 0. I thought it was a pretty efficient number to use. You could have used 1 or 2 or negative 5, anything that's on that interval. Anyway, when I plugged it into the derivative, I got a positive. So increasing on that interval. And then from 5 to infinity, I just chose the number 6. I like to make it easy on myself. I got another positive. So that looks like increasing, and I'm still increasing. Well, this question at the very last part asks what, at what points, at what x values do you assume local maximum or minimum occur? Well, look, when we go from decreasing to increasing, that's a minimum, okay? I've hit a low. So there's a local min at x equals negative 9 at that critical x value, okay? There is not a local extrema at x equals 5. because you went from increasing and then you increased again. So the no extrema happens right here, okay? And that pretty much answers it. The only other thing that you had to type in is like where you're increasing and decreasing, but we already stated this. So you're decreasing from negative infinity to negative 9, and you're increasing from negative 9 to infinity.